Why are we so concerned about quantum mechanics as it relates to black holes? Well, the existence of Hawking radiation presents an interesting problem to black hole physicists. Classical black holes can be characterized by three numbers: their mass, angular momentum, and charge. This is a concept called the no-hair theorem, which is a way of saying that information, which is what we mean by hair in this instance, can't escape from a black hole. But quantum mechanics tells a completely different story, which has led to one of the biggest unsolved problems of our time, the black hole information paradox. In addition to quantum mechanics enabling processes like Hawking radiation, it also throws a bit of a wrench into theories that try to combine quantum mechanics with general relativity. In particular, quantum mechanics requires information to be preserved. So in order for astrophysicists to have a complete description of a black hole, they will have to find a way to explain the so-called black hole information paradox. Information can be defined as something which is an answer to a question. When physicists talk about information, they're generally asking questions about the characteristics and state of something. So when we ask about the mass of a star, or we measure what its spectral output is, we're generating information. Now imagine that you're the commander of a scientific research vessel that's in orbit around a black hole, collecting measurements about the properties of the black hole. You can very easily deduce the mass of the black hole by observing, measuring, and timing how long it takes to orbit the black hole at a given distance. You can also measure the spin of the black hole by comparing the size of the innermost stable circular orbit to the size of the event horizon. And by dropping a couple of test charges and observing their behavior, you can tell the charge of the black hole. Scientists think that most black holes have zero charge anyway. So, as the commander, you've collected all this data, but oh no, you've accidentally crossed the event horizon. Luckily, you and your crew have survived, but the future is bleak. Given the fuel that you have in your reserve, you can only postpone your collision with the singularity by a few hours, maybe a few days at most. Is there any way that you could send what you learned back to a distant observer, or does the event horizon prevent information from escaping? Classical physics, that is to say general relativity, has very bad news for you. There's no way for you to transmit your data across the event horizon. But being a good spaceship captain, you are brushed up on your quantum mechanics, and you know about two important principles: quantum determinism and the principle of reversibility. Let's start by unpacking the easy one: reversibility. Reversibility is the idea that physical laws can be used to predict the future or the past of a particular system. If we look at a comet shooting by, not only can we predict where it will be decades from now, but also where it was decades in the past. In some sense, reversibility also tells us that we can go backwards from one state just as well as we can go forwards. In reality, we know that reversibility is more complex than that. Shattered mugs don't suddenly unshatter themselves. But we'll address that when we discuss entropy. On the other hand, quantum determinism is a much stranger idea. Determinism on its own is the idea that we can predict the outcome of any interaction if we have sufficient information. If I throw a ball and you know its direction and how fast it's going, where it lands is predetermined. But quantum mechanics basically deconstructs the notion of classical determinism because of a concept called the Heisenberg uncertainty principle. Since we have limits on what we can measure, we also have limits on what we can predict. Quantum determinism is then telling us a slightly different version of the story. We can predict with certainty what the probabilities of outcomes will be in quantum mechanics. Since the principles of quantum determinism and reversibility are fundamental to quantum mechanics, we've run into a problem. These two principles together mean that information must always be preserved. But the no-hair theorem for black holes says that information falling into a black hole disappears when it crosses the event horizon. Many scientists postulate that the information is destroyed somewhere at the interior of the black hole. In the next lesson, we'll delve further into this investigation, examining specific theories which attempt to explain the black hole information paradox. So, which is it? Is information preserved by quantum mechanics, Or is it destroyed by general relativity? There are many possibilities. The information could be destroyed. It could leak out of the black hole gradually. Or maybe information could escape in a powerful explosion. Perhaps the black hole itself saves the information like a giant hard drive. The sad truth is that we just don't know. Although there are no known laws that unify gravitation with quantum mechanics, many researchers, including Stephen Hawking, now believe that information is preserved somehow and deeply linked to the process of Hawking radiation. Some researchers have had other interesting ideas. One such interesting idea is the concept of a new boundary within the event horizon, the information firewall. In 2012, a group of physicists, Almhiri, Malroff, Polchinski, and Sully, shortened to AMPS, introduced the concept of a boundary of high-energy quanta that destroy all incoming information, the AMPS firewall. The AMPS firewall cleans up some of the inconsistencies of quantum mechanics by providing a mechanism to destroy or scramble the incoming information. But some scientists think that the firewall creates more problems than it solves. Present-day research done by Don Page at the University of Alberta suggests that the information firewall described by the AMPS group could produce a naked singularity. If indeed there is a firewall within a black hole, Page and his collaborators demonstrate that the firewall could migrate to a region outside of the event horizon, allowing the singularity to become visible to distant observers. We already know how much physicists abhor a naked singularity. One of Page's research collaborators, Misao Sasaki, has said, if a firewall exists, not only would an infalling object be destroyed by it, but the destruction could be visible even from the outside. This is a very complex idea, but it brings up an interesting motivation for physicists. If the firewall idea is right, it means that there is new physics for us to consider. If the firewall idea is wrong, it means that we've uncovered some potential flaws in older physical theories. Although there is no consensus about how the black hole information paradox will be resolved, there are several leading theories about the fate of information that has fallen into a black hole. One such theory, put forth by Stephen Hawking when he originally described Hawking radiation in 1976, predicts that the outflow particles from the black hole would have unpredictable properties. So then what does Hawking radiation actually look like?